Have you ever wondered how your brain actually learns? We often think we see the world objectively, but in reality, we are constant prediction machines. Welcome to the intuition behind Bayes' theorem, the mathematical framework for updating your beliefs when you encounter new data. In a world of uncertainty, Bayes is your best tool for clarity. To use this tool, we must first understand its mathematical heart, the Bayes formula. It states that the probability of a hypothesis A given evidence B is equal to the likelihood of the evidence given the hypothesis times our prior belief, all divided by the total probability of that evidence. P of A given B equals P of B given A times P of A divided by P of B. To understand Bayes deeply, we need four concepts. First, the prior, what you believed before seeing the evidence. Second, the likelihood, how well the evidence fits your hypothesis. Third, the evidence, the total probability of seeing that data. And finally, the posterior, your updated belief. It's a continuous cycle of learning and refining. Let's look at a classic medical example. Imagine a rare disease that only 1% of the population has. This is our prior. Now, we have a test that is 99% accurate if you are sick, but it also has a 5% false positive rate for healthy people. If you test positive, what is the probability you are actually sick? Most people instinctively yell 99%, but they are wrong. To see why, let's look at 10,000 real people. Out of these, only 1% or 100 people are actually sick, while 9,900 are healthy. Now, let's run the test. Among the 100 sick people, 99% will test positive. That's 99 real positives. But among the 9,900 healthy people, 5% will also test positive by mistake. That's 495 false positives. Now, look only at the people who tested positive. We have 99 real positives and 495 false positives, making a total of 594 positive results. To find the truth, we divide the real positives by the total. 99 divided by 594. The result is only about 16.7%. Even with a 99% accurate test, a positive result only means a 17% chance of being sick because the disease is so rare. This is the core of Bayesian thinking. A test does not work in a vacuum. The context, how common the event was before the evidence, matters just as much as the evidence itself. This logic is everywhere. Your email spam filter uses it to calculate the probability of spam given words like free or winner, updating its belief with every message. Think about self-driving cars. A Tesla or a Waymo is constantly receiving noisy sensor data. Is that blurry shape a pedestrian or a mailbox? The car combines its prior knowledge of road layouts with real-time visual data to update its probability map every millisecond. This recursive Bayesian estimation allows machines to navigate a messy world with high precision. In science, Bayes is the heart of the modern scientific method. Unlike frequentist statistics that rely only on p-values, Bayesian inference allows scientists to incorporate previous studies into new ones. This is crucial in drug trials and climate modeling, where we build upon decades of knowledge to reach robust conclusions. Ultimately, Bayes' theorem is a philosophy of humility. It teaches us that no belief should be held with 100% certainty, and that we must always be willing to change our minds when the facts change. As George Bach said, all models are wrong, but some are useful. Use Bayes to make your model of the world a little less wrong every day. References: E.T. Jaynes, Probability Theory, The Logic of Science. Richard McElraith, Statistical Rethinking. Sharon Birch McGrain, The Theory That Would Not Die.